I did not follow my protocol. Okay. So this is my neutral axis, right? So the 5,000 will induce a torque or a moment. So I'll draw for you how this will deform. So now the deformation will look like this. Okay. So is it a torque or a moment?
Moment.
Oh yeah, now it's a moment.
Sorry, Jacob, it's not you, okay? It's me, right? Now, I like that. Where are you, Jacob? I hear your voice, but I don't see no Jacob. Oh, wait. Why are your initials, Jacob?
JP.
JP. Okay, I still don't see you. You are in this class, right?
Yeah.
Okay, so Jacob, you just see the importance of drawing the deformation, yes or no, Jacob? Right?
Yeah, but I'm still like a little bit confused because isn't that like it's at the end of that rod that's sticking out? So wouldn't that cause like the neutral axis to twist?
But wait, it will also. It does both, Jacob. You are absolutely right. But we have to draw a different view to see that, Jacob.
Oh yeah, because we consider just the 3D or the 2D
Yes,
case.
yes.
Okay, I gotcha.
Yes. Okay. Oh, I don't know why. Every Friday, I'm very happy. Like I'm being a father again. You know, so happy. You know, every Friday. I did not buy any cookie, by the way. Okay, don't worry. So we know that this is listen, if we make mistake, okay, we make mistake here, okay, and it's between you and me and internet and the rest of your classmate. When you go to the industry, you make the same mistake, you know what will happen? I will look for you. Okay, don't make that same mistake. So now you know how to analyze. That's why when you make mistake, make it here. Okay, get it done with. Okay, I want you to be bold, to be try and know what is the right thing and what is the wrong thing now. Okay, because when you are out there in the wild west, okay, you will never know, okay, what is going to happen when we make wrong decisions. Okay, so I want you to learn. I like that. I love that. I absolutely love that. So again, now question for you guys. The perpendicular distance is towards the element or towards the neutral axis.
The element.
Well done. Okay, well done. Okay, why towards the element? Because the perpendicular distance is what? Parallel to the neutral axis. Or if we use what Mustafa say, the force is intersecting the neutral axis. Okay, so now, so this is Mustafa. Am I right, Mustafa? Mustafa, I got sleeping again. You know.
Yes, sir, you are correct.
Mustafa.
Eugene, should it be MX, the moment about X?
Oh yeah, where are you? Jasmine, you
Hi.
again. I owe you beer again. MX, you're right again. Okay. So it's 5,000. That's why I say when we make mistake here, right? Within our own family, right? And we will not declare this mistake out in the public, right? Like Harry and Meghan, right? You know what I mean? Yeah, we don't wash our dirty laundry out in the open. Okay. So 5,000 multiplied by 0.2. So that is 1,000 Newton meter, and it's going to be acting in this direction. Okay. So if this is the case, this is moment about X. Okay. So you know that stress X or element H will be compression, and it's going to be stress max, right? Yeah, because it's furthest away from the perpendicular. So now we do VZ. Okay. So VZ, you're going to have a shear force acting at 5,000 Newton. and is going towards the what? Going towards the right. Okay. So the last one.
Wait,
Yes.
sorry, I didn't mean to interrupt again, Professor, but isn't
no,
element
no.
H, isn't the compression on that 0 because it's not on the surface heading
Oh
towards like the
yeah,
dip?
well observed. No, I like that. Wow, I'm sleeping. Okay, so this is
It's all right.
0. Okay, you're absolutely right. Okay.
Does that mean I get a pint of beer?
Huh?
Does that mean I get a
Okay,
pint of
where
beer
are
now?
you? Where are you living now? Are you somewhere nearby?
I'm in Boston.
Oh, okay. Boston. Are you American?
Yeah.
All right. Be Canadian, okay? Okay. Where am I now? I don't know. If Trump come back, I don't know what will happen. But anyway, hey, stop this. Focus, focus. So we realize that the shear, right, is going to be at its maximum. Yes or no? Right. So this is where, oh, I do apologize. So this will be 0. You're absolutely right, Connor. Okay. Okay. So that's our VZ. Then we are going to view our last view. Okay. Connor, okay, I mean, you can don't answer this, but why McMaster, Connor? Any idea?
I'm a Canadian citizen, so tuition rate is better.
Okay, yeah. I mean, in America, you go to a university that is like top 5 or top 10, like in Canada, like McMaster is, before food. Okay, I'm telling you guys the truth. Before food, right? Before what you put in your mouth, the school fees is close to 30,000 US. Connor, am I right?
I don't know exactly what you said, but like it's it's a little too expensive around here.
Oh, okay, okay. I'm talking about the top 10 engineering schools in US of A. Like the Princeton. If you can come to McMaster, you're good in going to Princeton, okay? So this is our neutral axis, right? This is our element H, right? So now, if this thing were to deform, okay, if this thing were to rotate, okay, so if this were to rotate, okay, okay, so this is how I'm just drawing curve, okay, exaggerated. At the neutral axis, right? The neutral axis that we just drawn, it will not change at all. It will just what? Rotate. Okay, it will just rotate. So this is where you classify it as a what? As a torque. Okay, this is where you that's what Jacob found already. Okay, so when that's the case, you know that will be torque, but y, and the torque is relative to the to the neutral axis to the where the force is applied. So the torque will be equal to 5,000 multiplied by a distance of 0.15. Okay, so this is 5,000. So it's 750 Newton meter. Okay, and it's going in this rotation. Okay, so I think with these two examples, I think you guys did learn what mistake to make and what mistake not to make. Okay, so the shear is also equal to max, but the shear over here is equal to VQ over IT. The shear over here is equal to TR over J. Okay, now, any questions so far? We good? Okay, now the next one we're gonna do is like I love this problem. Okay, I love this problem. So now we're gonna do the full blown thing. Okay, now we're gonna do the full blown thing. Okay, so we are going to identify our normal force, shearing force, bending moment, okay? And if there's torque, we're going to find out torque. And then I hope by the time we are done, I want to construct the element. Okay, I like to construct the element. Okay, so we're going to put into formulas and we're going to construct into elements. Okay, so let's do that now. And this problem is a long problem. Okay, so in your test or your exam, one problem like this, okay, will take you easily, okay, 1 hour easily. Okay, or more, I don't know yet. Okay, but I'm going to teach you ways to do this that you will have the confidence. Okay, so confidence in your analysis is important. Without that confidence, okay, is pretty you will have doubt, and having doubt is the path to the dark side, right? Okay, so in Chinese cooking, okay, I'm trying. I mean, my ancestors were Chinese. Some of you do cooking also, Chinese type of cooking. Question for you guys: how will you ensure that your cooking tastes good? Anyone? Anyone cook Chinese food? No.
Just watch a
No.
YouTube video.
Ah,
Just watch a YouTube video.
you cheeky sort. Everything YouTube. You learn my course from YouTube. I'll come after you. I'll come after you. Okay. Have you tried learning my course from YouTube? Yes or no? Anyone? I don't mind. Okay. As long as you understand what is going on, I don't mind.
They're probably not here right now if they're watching on YouTube, right?
Oh, but YouTube is also my content, right?
Mm.
Okay. So this. 4 forces are applied to a W200 times 41.7 roll beam as shown. Determine the principal stresses or principal stress and maximum shearing stress at point A. Okay, so we are asked to determine, and later on I will tell you why they are interested in principal stresses, and I'll tell you why they are interested in shearing stresses, and especially principal stress. That is what material property that is of concern. Okay, the principal stress. Okay, so the principal stress can be tensile, can be compression, depend on the test that you've done. Okay, so here we go. So this table over here that you see now, okay, it's a table that you can find on the last few pages of your textbook. Okay, so this is where I got it from. And I want you to start looking at the terms now. Okay, the first term I want you to find, this is a what? Anyone? White flange shape. Yes or no? Now you know what is white flange now. All of you know, we just did that last week, right? So now you know white flange. When you see this term, okay, you know that this is going to be a thin wall analysis. Okay, in thick wall, we don't call it white flange box beam, right? We don't consider that. The only time we consider this is when we have a section, is a thin wall section. Okay, so be very observant with all this. Okay, let me describe more about this table. Okay, so is W400. Okay, and it's 41.7. So 41.7. I'm going to highlight this. Okay, so this is the data that we will be focusing on. Okay, these are the data. So the good thing about this, okay, once you have this data, okay, you know what I will not be testing you again already. So you know that what is our area. So this area over here is our cross-sectional area. Okay. Then D is our depth. So let me copy this figure. Right. So now you know that this is our our depth. This our depth. Okay, so the whole thing is 205, all in millimeters. Okay. Then the next thing is what do you call this? So now you guys have been